Section 9.1, page 496, Introduction to Matrix Methods of Linear Systems. So, they talk about chapter 5. It's really unfortunate that we didn't cover that section. It says, in chapter 5, we analyzed physical situation wherein two fluid tanks containing brine solution were interconnected and pumped so that ultimately to deplete the salt contained in each tank by accounting for the various influxes and outfluxes of brine, from one to the next, what's coming in. A system of differential equations of the salt content x of t and y of t in each tank, x of t in the first tank, y of t in the second tank, really gave this equation. Again, we really don't have to cover that. We just barely covered three main things though, but we didn't cover the rest of chapter 5. The applications we're skipping. If I look at that equation right there, I could say, you know what? That looks like dx dt dy dt equals negative 4244 times xy, or I could simply say that is x prime y prime equals negative 4244 multiplied by xy, or simply I could say x prime equals matrix A times x. This is called a normal form, something we're gonna want from now on. A normal form is when you could write a system of equations in terms of derivatives as a matrix equation. And we're going to start by just doing that in the beginning. For now, we're looking at this, okay, number 1 through 6, and this is on page, I believe is on page 500. It says, express the given system of differential equations in matrix notation. Just matrix notation. Well, if I really want to write this, wouldn't you say this, oops, not red. Let's go blue. Wouldn't you say this is xy prime equals, and remember, we want to put xy there. So how does that work? Isn't this saying x prime equals 0 x plus y and y prime equal negative x plus 0 y? So wouldn't that be 0 1 negative 1 0? And again, if you pay attention, again, that's all they want. But I'm going to add to this a bit. Do you notice they're going for this form, the normal form? And why the normal form? Because we're going to be solving that. But how about this problem? Wouldn't you say this is x1, x sub 2, x sub 3, x sub 4 prime equals A, and we're going to list x1, x2, x3, and x4. So you want them in order. x1, x2, x3, x4, x1, x2, x3, x4. That's simple. x1, x2, x3, x4, and there it is. And again, that's really x prime equals ax. They really don't talk about it until the next set of problems. And how about here? The same deal. Wouldn't you say this is x1, x2, x3 equals x1, x2, x3. Again, we're going for x prime equal ax. And here, isn't that cosine of 2t 0, 0, 0, sine of 2t 0, and 1, x2 and x3? And there it is. Now, what if you have higher order differential equations? You reduce them down. This is the trick that we use, and I'll show you how that works. And you could do this not only for second order, you could do this for third, fourth, fifth. We're going to focus on second order only for now. If you want the normal form of higher order differential equations, what you do, you let y equal x1, right? If you're talking about velocity, you let y equal v, and y prime will be v prime. You reduce the power by 1. If I take this right here and I say, you know what? Let's do that on this problem. If I let y equal x1, I need to go to a second derivative. So if I take a derivative of both sides, I'm going to call that x2. And if I take a derivative of that, wouldn't that be x2 prime? And that's really how we play the game. Now watch what happens. I'm going to take this equation right here, and I'm going to say, well, look, this equation now just became 1 minus t squared. Y double prime is really x2 prime minus 2t. Y1 prime is x2 plus 2, and y is x1. So I convert the equation into x1 and x2 only, with reducing the derivative by 1. And what I'll do, I'll say, all right, well, look, if I really want to talk about x1 and x2 prime, that's going to be and aren't you going to let x1 prime equal x2? So wouldn't you say that is 0, x1, x2? And how about x2? What are you going to let x2 prime equal? Well, right there, solve for it. Wouldn't you say x2 prime equals negative 2x1 plus 2tx2 divided by 1 minus t squared divided by 1 minus t squared? So for x1, that will be negative 2 over 1 minus t squared. And for x2, that will be, I have all the space in the world and I keep on shrinking this. I don't know why. That will be negative 2 over 1 minus t squared, and that will be 2t divided by 1 minus t squared. And there it is. Right? That's really x prime equal ax. And if it was an x to the third, I could have did that more, you know? I'll take a derivative. I'll let this be right here, x to the third. And I'll take a derivative, and I'll keep on doing that. It's a simple trick. But it allows you to convert differential equations, any differential equation, to a matrix equation. And the same deal here. And those are extremely important equations. So how does that work? If I really look at this, I'll always start by let y equal x1. Take a derivative. Set that to be x2. Now look at those two. If I take a derivative of that, wouldn't that be x2 prime? And if I was going to go higher, we're not in this class, but we do that in other classes, then I would let this be x3, and I'll say y triple prime equal x3 prime. And that's really how it works. But for now, we're going to only focus on second derivative, which is really simple. So how does that work? I'm going to take this right here, and I'm going to say that is x2 prime plus 1 over t, and y prime is x2, plus 1 minus n squared over t squared, and y was really x1 equals 0. And if I write this in my, in my normal form, x prime equal ax, I'm really looking at x1, x2 prime equaling. And if you notice, x1 I'm sorry, x1 prime is really x2. So this is the column for x1, this is the column for x2. And x2 is actually what? If I solve for x2 prime, wouldn't this move to the other side? That would be negative 1 over t times x. Oops, backwards. Wouldn't that be n squared over t squared minus 1, because when you move it to the other side, times x1. And when you move that to the other side, doesn't that become negative 1 over t? And there it is. And that's all we want to do for this section. And you're going to do this, the homework 1 through 9. I just want to warn you about number 7, I believe. 7, they let y equal v. You don't have to. You could call it x1 if you wish. And they take a derivative, right? And they call that, I messed up. I knew I messed up. They let y equal, again, you don't have to do this, but that's how they have it in the back of the book. They have y equal v prime. And when they take a derivative, and that's really how they do it. You don't have to do it that way. You could do it with x1, x2, but this makes more sense. Whatever works.